Start. Tonight we want to cover basics of image processing and point operation. Mm. So we will first understand what an image is and how images are formed. And then we will understand how to manipulate pixels in these images through so-called point operations. So these operations are available in popular software like Photoshop or GIMP. They deal with increasing the amount of light, for example, in the image, amount of brightness, darkening the image, enhancing the bright vibrance of the image, those kind of operations. They are also useful in industry also. So these are basic ways of manipulating images. So that's the plan. There are some quizzes also on the Moodle. So when the time comes, I will open the Moodle and ask you to do the quiz. These are very simple questions. The Moodle. Yes. What is a digital image, first of all? A grayscale digital image is a rectangular array of numbers which represent pixels. Each pixel can take an integer value in the range from 0 to 255 for an 8-bit image. Now, these numbers at each location of this image are of 8 bits in size. So you know that 8-bit numbers can represent 0, 0, 0, 0, 0, 0, 0, 0. That means 8 zeros. That corresponds to 0 and 1, 2, 3, 4, 8 ones, right? 8 ones correspond to 255 in binary. It corresponds to 255. So those are the numbers that can be represented by each of the pixels in a grayscale image. Grayscale images are, grayscale. They are not color images. If the image is a color image, then there would be 3 such arrays. So the size of this array is actually the resolution of the image. For example, if you take a newer camera, it will have a resolution 3712 times 5568 or so. These are high resolution images. So we take the top left corner as the 0, 0 and vertically downward axis as the y-axis or the x-axis. So here is a pictorial representation of that. So you can see this is 1, 2, 3, 4, 5, 6, right? 6 times 1, 2, 3, 4, 5, 6, 7, 8 images. So this is a 6 by 8 image. It's a very small image compared to these large images that we get from cameras. So if you take this pixel, okay, this pixel, that pixel we identify as pixel 2, 3. You can see the first coordinate or the I coordinate is 2, the J coordinate is 3. So first axis is from vertically downward and the second axis is horizontally rightward. So please remember that, and that we start counting from 0, 0 from this pixel. I hope that is clear to you. Okay, so if you take a color image, there are 3 such arrays. So these 3 arrays, each plane corresponds to blue, green, and red. So you can see the blue plane, the green plane, and the red plane over here. Um, if we access a pixel at location, for example, 2, 3, we will get 3 values. Those 3 values are B, a G, and R. A value for blue, a value for green, and value for red. So each of these values can be from 0 to 155 because each one of them will be an 8-bit number. So in this context, 2 to the power of 8 times 2 to the power of 8 times 2 to the power of 8, different colors can be represented in an image. Okay. So this is a color image. Then one question is why BGR? Why BGR? Then I'm calling these are the primary colors, right? I'm calling blue, green, and red the primary colors. But in school, you were taught that the primary colors are okay. Maybe shall I ask you a question? So in the chat, can you type what are the primary colors?
Red, green, and blue.
Red, green, and blue. In the school, in the art class, what were the colors that they taught? In the art class,
Red, yellow, blue.
red, yellow, blue, right? Something like red, yellow, blue. Yeah, those were the colors taught in the art class. These colors are different. What's the difference and why the difference is there? So in the art class, yeah, so there's a piece of paper, okay? There's a piece of paper. Assume that there's an A4 sheet, white sheet. What you do is you take the whatever the red pastel or something, okay, red pastel, and you draw a line like that. What you are doing is from the colors this uh, sheet has, it has all three colors because it's a white sheet. You are taking off all other colors except red. Can you see that? So by drawing using the red pastel means taking all other colors off except red. So these colors are called subtractive colors. Subtractive. Subtractive colors. From a white sheet, you subtract out colors. But in the computer screen, your computer screen is black, right? You use LEDs to light up and it produces a color by addition. So these colors are additive colors. So additive colors. So I hope you can see the difference. So in a TV also, it's a BGR. Yeah. So why don't I say RGB, not BGR? That I'll tell you very soon. Okay. So now once again, image resolution, number of pixels in an image, it's a width and height. So if you, for example, if you take a full HD image, 1925,080, actually I should switch these two numbers. It is a 2 million, about 2 million pixels. That's why a 2 megapixel image is called an full HD image. This impacts image detail and sharpness, file size, and the processing time. Then what is the thing called dots per inch? Does anyone know what the dots per inch means, DPI? If someone is familiar with the printing industry, he or she will know. So dots per inch means you take the image and when you print it, how many dots do you print per inch? How many dots do you print per inch? To get a good print quality, you need 300 dpi. 300 dpi. So that means if you're printing at 300 dpi, if you have, for example, let's say you have a 4-inch, all right, by 6-inch image, you need uh, the resolution of the image to be 6 times 300 and 4 times 300. That's the resolution you need. So that means you need 1200 times 1800 image to get a proper 4 by 6 image printed. So if you just zoom and somehow print, you will see the pixelations. The print will not be nice. But for online display, 72 to 96 will be sufficient. Yeah. Okay, so this is very important if you want to get a good quality print of a picture. Yes. That's why you have to use expensive cameras in photography when you want to get a good quality prints. I hope that's clear to you. Okay, so now we will create an image and I will show you how using Colab, Google Colab, how to do that. So I request you also uh, to do this with me. Contrast ratio is it's a property. Someone is asking what is contrast ratio. It is the property of the screen. It is the intensity difference between the blackest level and the brightest level. It is a property of the display screen, actually. Okay, so now let's Thank you for that question. I very much welcome those questions. So first of all, let's do this coding. So after we do this, you will realize that you need to know a little bit of Python. Then I will show you a tutorial also of how to do that. So let me go to my escape here from this slide set, and then I will go to Google Chrome. Okay, uh, on your computer, please do this right now and type Colab. It's called the Google Collaboratory. In Colab, we can type code, but later on, I will show you how to do that on your own computer rather than using Google resources. So please type Colab and hit enter. Then you can go to Google Colab, colab.google. Colab. So this is what you are typing on Google Colab and go to the Google Collaboratory. Colab. So I'm going there. So here you have given two options: open Colab or new notebook. So I will say a new notebook because I want to start something new. Okay, so it will start a notebook. So these things are called notebooks. So some of you may know you can type code and run them here. It's very easy. Okay, so it has not been saved, so you can save it by typing EN5204. I can write 2026. I like to save them properly. 26 month 7. Yeah, within class version. Okay, so I saved it. There's the file. Okay, so now I'm going to start coding. Is this visible, everyone? Are you able to see the screen?
Yes, sir.
Yes,
Yeah,
sir.
excellent, excellent. I hope you also doing. So please type the code in the slide. Import CV2 as CV. So this is importing the package called OpenCV, which we use for image processing and computer vision tasks in this course. And you hit enter. And then there is a numerical computation package that also we import, means you are saying that you are using that. Imports that, import numpy as NP. So it is doing AI prompting also. Please do not use the AI prompting yet. You can please type it out. Okay. Then to display these things, I have to say import matplotlib dot pyplot dot as plt. Okay, now I have imported the packages that I need. Then I'm going to create an image. I'm going to create that image as IM is the image name is. From the numpy, I'm going to get zeros. np dot zeros. I'm going to create a zero array, zeros. So I have to tell the size of that array, size of that. So what I'm going to do is I'm going to create a 6x8 image, 6x8 image. And I have to tell what is the data type that I'm using in that. So data type is extremely important because D type equals np dot uint8, not unit8, uint8. Uint means unsigned 8 integers of 8 bits. Uint8 means unsigned integers of 8 bits. This is creating a 6 times 8 image of 8 array of zeros of data type u in unsigned 8-bit unsigned integers. I hope this is clear to you. Okay, so it's good to run this and see whether there is any problem. So you by clicking this play icon, you can run that. So it has run, and there's a little tick here that means it has run that. But I did not display anything. All right, now I'm going to access one pixel there. IM, as we showed in slide 2, 3. I will take 2, 3 and put the value, the full white value, 255, the maximum value it can take. I'm putting 255. Now I have to show this image on the screen. So to do that, I say figure AX. So it is a little bit of cumbersome code. PLT dot subplots 1, 1, just one subplot. So these are actually uh, annoying code, but uh, yeah, please, we have to do this. Mm. So then we had to show that. So in this axis.imshow is the command that you know. I am using displaying my image there, and I have to give some information. CMap, color map is I'm using the gray color map, and I had to say the maximum and minimum values. Vmin equals 0 and Vmax equals 255. 255. That's done. So after that, I can say plt.show. Also, I can put the tick position at the top because that's where my axes are. ax.x-axis, x-axis, set ticks position, and I can put it at the top. It's just a axis manipulation. So now if I run this, you will be able to see this small image. So we can see that small image, pixel 2, 3 is fully bright. Maybe I can make this a little bit small image. Okay, so you can see what we wanted to achieve. Any questions about this? So please do not hesitate to ask questions. Okay. Yes, so I will give you a couple of minutes for you to do this. Please do this on your own. Do not copy and paste from the slides. I know slides are available on uh, the Moodle, but please do not copy paste. Type on your own. So in Python, this hash symbol, that's a comment. I have written a comment there. So you can see. This is just a display part. There's nothing to do with image processing. Only two commands, only two lines that you need to know are these two lines. Is that okay? All right. So let me ask you a question. To make the pixel gray, pixel 2, 3, 2, 3 gray, what should I do? So can you answer that? To make the pixel 2, 3 gray, what should I do? Will someone be able to answer that? Okay. Maybe if I put a value like 100, it will become gray. Can you see that? So the maximum value is 255. If I 100, so if you put 0, it's dark, right? You won't even see that pixel. You see just black. Yes. Yes. Okay. I hope that's clear to you how to create this uh, image. So I can put a text here and type what I did there. Mm, uh, creating a grayscale image of size 600 times 8. Yeah. So you can see you can write these kind of things also in notebooks. These are called Jupyter notebooks. That's why the extension IPYNB, Jupyter notebooks. Okay. So now our task is to create a color image. So on the slide we saw that next is color image. So rather than saying 6, 8, I have to say 683. These are the three colors RGB. And when I set the pixel value, I need to give three numbers. Yeah, so it is very easy. So we can use the same code. So I will not type again. So I will use the same code and only do the changes, cut it. And I have a code block here. Click this code thing. I paste it. So now I put 3 here. X the error for of zeros, so data and integer. So this is right now. That's okay. So now I had to give the three numbers. So RGB three numbers. So maybe about 200 red, little bit of green maybe 100, and okay BGR blue. The blue is too much. Blue 100, BG green 100. I mean let's say 50, and red little bit of red maybe 200. And let's see what color this is. Now our color map should not be gray. We have to remove that. So we can see the blue VGR. Let's increase the blueness to. Okay. So now you must be already seeing something crazy here. This is, although I'm saying BGR, this is not BGR. This is actually RGB. The reason is this is the matplotlib's interpretation. I will show you OpenCV's interpretation later. So if I want to increase red, too much red, RGB also will reduce. Okay. So now it is you see a red pixel, mostly red pixel. In this one, it is RGB representation. Okay, so I hope these two pieces of code are okay for you. Any questions about that? Yes. Okay, so please do this and be happy that you have been able to create your first images. Okay. Now what we want to do is to open an image. Open an image that is in my Google Drive. Okay. So in the name, so this, let me type this. Type this one. I can insert a text block here. Creating a color image of size this one. That's what I did. And then opening an image. Next one is opening a color image in the Google Drive. So first of all, I'll show you my Google Drive. What is there? I have an image folder there. So there I have some folder. My drive, in my drive, I have a folder called images. These are beautiful sets of images. I have collected them for many years. So these images are there. So we will open this image, mr.jpg, which is in my images folder. So this is what I'm going to do now. So I add a code block again. So import CV2 as CV. Then, okay, if you want to display it, you need import matplotlib.pyplot as PLT. Matplotlib. Okay, now I can open the image. To open the image, I must mount the drive. So this is, I did not do that yet. So, okay, I'll go to a insert text block, mounting the Google Drive. See, this Colab does not still have access to your Google Drive. We have to remember that because Google Drive is something secure. So here I'm going to do some AI prompting. Mount my drive. I'm going to do this prompting and ask it to give me the code because I don't want to trouble myself for mounting my drive. So from google.colab import drive mount content drive. So this thing the AI gave me. So I'm going to run that. Then it will ask me for permission. Permit this notebook to access your Google Drive. Connect Google Drive. I give it permission. Then it will ask several questions. Review Google, whatever. I know it's correct. So I continue. I don't know this. I didn't want to read, but I gave it permission now. So now its drive is mounted. It will mount. Now it has been mounted, it says. So now you can see on your left hand side, my drive has been mounted. Can you see that this is my drive? And there you will see my images folder somewhere. Whatever, it's there. Images folder is there. Maybe you cannot see it, but it's for some reason you cannot see it. Yeah, images folder is there. See, images folder is there. Okay, so now I'm going to access that. So I'm going to say im equals imread cv dot imread. So I'm going to use OpenCV's function to read the image. Okay, now it's giving the way to do that. So you have to say the same thing there, content, drive. So after that, you saw here, after that drive, I had something called my drive. My drive. My drive. Inside the my drive, you saw the images folder that I created. ima.jpg is that. Then I had to tell it the mode to which you open cv.imread color. I open as a color image. I can open it as a grayscale image also. So after opening that image, it's always good to check whether the image has been opened. For that, I can write assert im is not none to ask whether image has not is a null value still, whether it has not been opened. It has been opened not now. I have to for these AI prompts, I'll say yes. So I create an axis and I want to show the image. I think im show is sufficient. These things are not required, and I'll remove the text. Okay, let it be. plt.show. Okay, this is the way to open it, and you'll be able to see the image of Emma Watson. Are you ready for me to run, or do you want more time? Okay, let me run it and show you. And there'll be a problem, and then see, image is there. It's like an 800 by 600 image, but the colors are wrong. So we will understand why these colors are wrong and correct it soon. So until then, so please try this. I hope I'm making sense to you. Any questions? If you have any questions, please don't hesitate to ask. Please do ask, and we please get this done so you can have the Zoom window here, and then you can have your Colab window on the same machine, and please type the code.
So, small question: that MR.jpg is it available for download somewhere?
So it is an image I put in the images folder. You can create an images folder and put some image there.
Okay.
You can put some image. Yeah. These ones I'll give you as a gift for participating in the class. Later on, I'll give you these images. You can see these are beautiful images. Right? I have collected them for a long time. I'll give you those later. Right now, you can put some image in your Google Drive images folder. You can create an images folder, which you can see I have my drive images folder. There I have these images. So any of these images I can open. If I want to open this image of Ryan, I can open that. Ryan. But it will display, but you can see the colors are inverted, right? There is a problem there, these colors. So I will show you what that happens, why that happens. Colors are inverted. The face that should be in color is blue. Okay, here is the code. I'll give you some time to be able to write it. So if you have any question, please don't hesitate to turn on the mic and ask. I would very much welcome that. And you know that I do not like this online mode. I like to do the class in person, but every month, every week, people say that you cannot come. I'm recording this lecture, so I'll upload that also. You'll be able to see it if you miss anything. Okay, who needs more time? Does anyone need more time? If so, please let me know. Question. I had credential propagation was unsuccessful while importing the drive. That means you did not click maybe that the message that when Google shows ask you for permission, maybe you did not give permission or something. Uh, that's what I think. But if that doesn't solve, what you can do is put that message in ChatGPT and ask what is the reason. There shouldn't be any reason actually.
Okay, sir, I will check.
Pardon me? Yeah, please check it. Otherwise,
Yeah,
you can
okay, sir,
share
I
the
will
screen
check.
and show me. You can share the screen and show me if you cannot resolve it.
Yeah, okay, sir.
Then please share the screen and show me. We can have maybe others also are facing the same problem. We can see why. Let's see. But we can see your Zoom screen. Okay. Yes. Okay. Did I have that part of the code? I didn't have that. Or this that is
No,
not required. Only the first two lines are required.
yeah, sir, I put from get from the
Run it. Run it.
ChatGPT.
Okay. Run it and see. It's done. That's correct now. So, that's not the one. That's the table. So you have to click this button. This one to see the drive. You can click the button somewhere here. Here, this one.
Okay.
Okay, now you can see it.
Okay, thanks.
Okay,
Thanks.
excellent. Yeah, I appreciate this actually. Thank you very much for showing that the screen and getting that resolved. Thank you. Oh, it's all my emails. All the important things have been revealed to you. Okay. Yeah, so this is good. So anyone, if anyone has a problem, please let me know. We can resolve it right now. Okay, then I'm assuming that you all have been able to mount your Google Drive and open some image and display using this little command, imread. But one thing we have not been able to resolve, that is the changing of this color. Okay. So I'll tell you what the problem is. The problem is this. We are opening the image using OpenCV. Can you see that? cv.imread. cv.imread. We are opening the image using OpenCV. And we are displaying the image using matplotlib commands. plt means matplotlib. So that's the problem. OpenCV represents images using BGR key. Matplotlib represents using RGB. So what we open, Matplotlib thinks it's RGB. That's the problem. So they had to do the color conversion before displaying this image. So I will say here cv dot cv dot cvt color, convert color cv color BGR to RGB. So this is correct. So I'm converting the color of the image to from BGR to RGB to just to display. So this command is very important if you want to get the colors right. When you display an image using Matplotlib, when you have opened it using OpenCV.
So what's the disadvantage of using Colab versus on the machine?
It's a good question. Why do we want to use your own machine? So, but like it's Google Colab, right? You want to run your programs on your machine, right? So you want to become a proficient programmer, right? So you cannot be connecting to Google and using that. You want to have the different packages installed, and you have to have your own Python system and run your codes on your machine. So maybe your machine has a GPU. You want to use that. They allow some GPUs to be used, graphics processing units to be used. When you have the things installed on your machine, you can connect to remote servers. For example, when our students were my computer's workstations are in the university. They connect to these workstations remotely using their Visual Studio Code. So that's how they do it. So that's a very good question, and that's the reason.
Thank you, sir.
And we do not want to use other people's resources, right? And it looks very lame when we don't have our own computer with the computation stuff. That's the reason. So I hope you understood this reason for the color conversion. Yeah, this reason. So this CVT color. You have to use this one. Okay. Okay. So now the very first things that we have to do, that means creating an image, creating a grayscale image, and creating a color image, and opening an image, opening a color image in the Google Drive. All these things we achieved. Yeah. Okay. Now the gentleman asked an important question. You may have seen that I have linked a little video that I recorded last night. on installing Python and VS Code on your machine. So I'm not going to show it now because it will be very cumbersome for you to do it while you are in the class. So please go to this link and watch the video and install it. Or you can install Python. Use ChatGPT to ask for the steps that we can use. But this is a 12-minute video. You can watch that. Yeah, so I'll show you the steps of how to download Python to check whether Python has been installed, and then install Visual Studio Code, and creating a virtual environment, and getting things running. I'll show you. So then after that you can do this work. Thing that you need after installing this Visual Studio Code is installing OpenCV. For that I have given you the command in the, oh, I lost that command in the Moodle. I have written that command to install OpenCV. So you have to type pip install OpenCV Python. Pip install OpenCV Python. In the video, I show how to install many packages, like NumPy, this, that, and so on. In addition to that, type pip install OpenCV Python to install OpenCV. So please watch that video carefully. It's just a 12-minute video. Okay. All right. Now let's do the quiz. So please click this one, and it's a very simple quiz. Some person has already attempted. You can do the quiz and see. Very simple questions. Okay. For example, this one. I don't know. I think maybe in your one the question switch. I think. What is the primary difference between image processing and computer vision? We did that last time. There is no difference. Image processing enhances images, computer vision interprets them. Computer vision converts analog signals into digital and wrong. Image processing is used only in photograph. Image processing needs machine learning and computer vision doesn't. So this is the correct one, right? That's the correct one. That's the correct answer. So second question. Which of the following is an example of computer vision tasks? Of a computer vision task. Gaussian blur is image processing. Histogram equalization image processing. Padding image processing. Semantic segmentation is a computer vision task. I hope you remember we looked at SAM2 also. SAM2 is semantic segmentation, right? Facebook's SAM2 tool. Indeed, I think. Then third one. What is the goal of early vision in computer vision pipeline? So you have early vision processing, extracting high-level semantics, not correct, extracting low-level features like edges and textures, rendering synthetic scenes, creating 3D point clouds, compressing video. So this is the correct one, right? This is called early vision. Yeah, please ask that question also. Then next question: which of the following best describes the structure of this course? Oh, this is the wrong course name. It covers only industrial inspection techniques. It focuses entirely on deep learning for image generation, includes image processing, 3D vision, and vision methods. Image class in image processing. It's hardware-oriented course. Yeah, these are these course name is wrong. What is the following recommended to success? Use MATLAB and ignore Python. Avoid reading papers, just follow lecture notes. Memorize all the equations before exam. Implement at least one algorithm before the next class. I told that in the last class. Yeah. Okay, very easy. This is wrong. What is the advantage of using PyTorch in this one? So I did not teach that part. It supports dynamic computation graphs and deep learning libraries. So this is the reason. Only works with C++. It has hardware simulation. It optimizes only for image processing. It requires no coding. So this is a deep learning part. We will use PyTorch. That's the answer to that question. Next one. Which of the following is a real-world application of computer vision? Applying median field. It's an image processing application. Detecting faces in surveillance footage. That's correct. Printing high-resolution images. Image processing. Converting RGB to grayscale. Image processing. Saving images. Then nothing. Yeah. Then question number 8. What is an example of a generative modeling vision of optic flow, that is computing motion, not a generative one. Histogram matching, not a generative, it's an image processing operation. Bilinear interpolation is a simple image zooming thing. Sorbel edge detection is edge detection. Diffusion models, we talked about the last time. To generate images, people use diffusion model. That's the answer to this question. Question number 9. Which of the following is a typical use case of segmentation in vision systems? Image segmentation means taking a part of the image, extracting that, right? Estimating the motion of objects, converting images into JPG format, enhancing the brightness of images, add color to grayscale images, detect boundaries between different regions of images. This is the correct answer for that. Finally, what is meant by self-supervised pre-training in deep learning for vision? Learning meaningful representations from unlabeled data using surrogate tasks. That's the correct one. Use reinforcement learning to train vision models. That's wrong. Supervised training using multiple GPUs. It's self-supervised or not supervised. Training model on random images from the internet. That's not right. Learning from labeled data set. It's not labeled, self-supervised. So, like that, you please do the quiz and you'll be able to submit this like that, and you'll be able to see. Okay, so do quiz 1. Quiz 2 is also available that you can do at the latter part of the class. Okay, so I'll give you a few minutes to do the quiz number 1. It's very easy. I showed you the answers. But not for other quizzes, I will not show the answers. Okay. Okay, I hope you answered the quiz. Many people have answered. Yeah, a lot of people have answered. Oh, not all have answers. Yeah, please do it and submit that. It's very easy. I showed you the answers. Some more time. 3 people, only 3 people have submitted the answers. If you have made mistakes, you can take another attempt on the quiz. Yeah. If people have done. Okay. Yeah. When few more people are done, we can start the lesson. Okay.
So I couldn't get my picture to change color. Can you share the code again?
Yes. So you can see here this CV convert color. That's the one that does that.
Okay, let me check that.
This part. Yeah, thank you for that question. Okay, then we will progress as many people have finished answering. That's very good. Okay, yeah, we have answered. So we progress. Yeah. Okay, so one thing is you can display images using OpenCV. So here we are using matplotlib, right? You can use OpenCV in this fashion, like cv.name window. By using this technique, you can do that, but you cannot do that using Colab. Okay, you have to use Visual Studio Code in your machine to be able to do that. We will do it later. Okay, so then we can display image properties. If you like, you can say print in shape, image D type, in size. So we can do that also. We can do that in the Colab. So for the same image, I can open another coding cell, print. You can say in dot shape. So those things are there in the slides. Displaying the im shape, im d type, im size. Let's display the size of the image. In dot shape. It will print the shape. You can see 810 by 620 by 3. So we can see about 810 pixels in the vertical direction, about 720 pixels in this direction, and it's 3 means it's an RGB image, right? So that's nice. Then we can have the data type display. Paint the type. Comma im dot d type. It will display the data type. It must be in date, you can see. And I have written the image of size also here. That is just gives you the total size number of pixels, I think. So you can see that it's good. So this is what we covered up to now. Okay. So now what I want to do is to increase the brightness of the image. So in order to do that, I do this. I'm using this one, brightness increasing, using this command, cv.add, this one. Using this command, I'll be able to increase the brightness of that. After increasing the brightness, you can see I have created now two axes, subplots 1 and 2, and then I can access the 0th axis and the axis number 1. So in the 0th one, I'm displaying the original image in 1, which I opened, and in this one, that the change one I'm displaying in as in 2. Okay, so let's do that. You can do the coding. So let's open Emma's image in grayscale. So those codes I'll copy. But now I want to say imread grayscale. Grayscale. And I want to do write this as im1, and then im2 is equal to cv dot add im1, and I made that 100. And now I want to display them. Display both of them. Fig comma ax equals plt dot subplots 1 row 2 columns, fig size. I can say 10 by 5 or something. Okay. All right. So in AX0, I'm showing im im1. Of course, when you're displaying grayscale images, you know that you need the color map. CMap equals gray. And we have to give the Vmin and Vmax, right? Vmin equals 0, Vmax equals 255. Otherwise, this matplotlib does its own scaling of color. Im2 in axis 1. Yeah, that's okay. plt.show. Okay. So let's see what happens here. So you can see the brightness has increased. So I want to get rid of these tick marks. Now I don't need no tick marks. Remove ticks. ask it to give AI prompt. Oh, it's not prompting. He's not giving the answer. I don't know why AI is not answering. Robotics. Doing it. It's not doing it. Oh my goodness. That's not what I want. How can I get rid of that? Oh my goodness, I ruined it. Oh, can I delete it? Cannot even delete it. Does anyone know how to delete this?
There's an option about that.
You want that? Ruin my thing. Yeah. Yes. I should never use this AI thing. Oh, it's ruining my life. I don't know how to remove. Oh,
Control is it?
control is it? Yeah, yeah. Undo. Oh my goodness. Oh my goodness.
So I think if you go to the top edit, it might have the revert button, is it? On the top, next to file edit view.
Too much trouble, right? Hmm.
Or you can just delete, copy what you want and delete the rest.
Yeah, yeah. Revert this change. Revert this change. Yeah. Okay. Fine, fine, fine. I'll do it myself. So yeah. I don't use the Gemini prompting. I use Answer for something. Yeah, I had that in the slide, I think. Remove the access. Yeah, yeah. This is what I wanted. See, that already had. Oh my goodness. In my life. Oh my, not letting it go. All these things are recorded also.
The rewrite in a new code block. The code block is controlled by Gemini.
Code block is controlled by Gemini. Okay. Delete it, right? Yeah, okay. Got done. Done. Yeah. Okay, at last. At last. This nicely. This is what I wanted. Yeah, okay, so now it's nice. Okay, now this operation you understand, I added 100 to the image, so every pixel's brightness increased. Okay, all right. Is everyone okay with that operation? I hope so. Okay. One thing is now I'm tempted to do this. I'm tempted to do this. Rather than doing this one, I want to say M2 equals M1 plus 100. I want to add 100 to each pixel. 100. Okay, now you see what will happen, what happens. It's horrible, right? It's horrible. It's horrible. What has happened? What has happened there? Okay, so what has happened is when I added 100, the brightest parts of her face also got 100 added, and they went beyond 255. So beyond 255 means this uint8 format, that means 8-bit format, cannot represent those numbers. So it reverted back to 0. That is what has happened here. Any number greater than 255, it puts as 0. This is what happened there. Okay. So therefore, just adding 100 will not work. Incorrect. This is incorrect. Yeah. So this is correct. Now it's better. So I hope you understood that. Any questions about that?
So when you add the 100, the correct way, shouldn't it do the same thing? The behavior should
No,
be
the
the same way.
OpenCV is doing that. No, it is doing the right
Intelligently.
feeding. Not intelligently. You can see it has prevented that overflow. You can see it has kept them as white here, right?
Yeah.
There's no intelligence. It's just increased, but when it is going greater than 255, it kept at 255. So you can see this whole her face area is fully white, total white, right here.
All right. Okay.
Yeah, yeah. So that's what it's doing. So yeah, that also you can notice that. Okay. So this is what I'm showing there. So I hope you understand that. So the reason is these 8-bit numbers, as you know, these are uint8 numbers. So therefore, they have only 8 bits to represent a pixel. So what happens is when it goes 1, 1, 1, 1, 1, 1, 1, 1 is 255. If you go beyond that, it is not able to represent, so it has put 0 there. Actually, it should have put 0. It should have done modulo. That means 255 plus 1, 0. 255 plus 2, it should have put 1 there. But it did not do that, but that's okay. Okay. So one more thing that I don't want to show you now, but you can do it at home, is you can, rather than using these functions, you can do it in a loop. But if you when you do that in a loop, it's very slow, because these languages like Python and so on, they are very slow with loops. So this is slow, so please do not do that. You can see this loop I goes from along the x-axis of the image. So if you take this image, that's how it looked like. So this is the y-axis, as we discussed at the beginning today, y-axis, and this is the j-axis. So y-axis will go from 0 to image shape, right? This is the number of columns, rows, number of rows. This one is number of columns. Number of columns. So it will, this loop will, I will go this way, j will go that way, and then I can access im ij. It is im1 ij plus 100, because I have I and j from there. That's how you do that using a loop. But this is not something that we do. We use OpenCV functions for that. Those have been implemented in C++. Okay. So now let's try to extract the color plane of an RGB image to know something about color. So here you can see I'm doing something like this. I have an image opened, a color image, this one. This is the original image I have opened. And then I made a copy of that saying in blue copying that. So this image one is copied now. And then to keep the blue one, what I did was, now first axis is the I, right? This is the I axis. This is the J. These are the 3 color planes. So we know that when you open the image in OpenCV, it's BGR. So B corresponds to 0. G corresponds to 1. R corresponds to 2. What I'm doing is all I's. This means all. This colon means all. All I's all j's, the first color plane means green. Green, I'm setting that as 0. And then all rows, all columns, the second color plane, which corresponds to red, I am putting as 0. So that means I'm putting zeros for the green plane, zeros for the red plane. Therefore, what remains will be only the blue part of the image. Yeah, so you can do that on your own. Maybe let's do that, right? Let's do that just for the sake of doing that. Let's do that. So we have some fun. Open the color image and do this. So what image should we open? Is there a colorful image? Yes, there's this colorful image, RGB flowers. That's what I'm going to open. Import CV2 as CV. Import matplot lib.py plot as plt, and then im equals cv.imread. Okay, I need the drive location. Then my image is RGB flowers .jpg. So I will open this as cv.imread color. Okay. Then always when I open an image, I need to assert im is not none. Otherwise, a lot of trouble. Okay. Now I am going to make a copy. Im2 is im.copy. Is that what I did in the slides? Yeah. Okay, I called it in blue, right? In blue. Blue. In blue, im.copy. Okay. So then I want to say in blue, all the rows, all the columns, plane number 1. That is, I'm setting that as 0. So this is BGR. So 1 corresponds to green, right? So in blue, all the rows, all the columns. The second one is also set as 0. So the same thing. So it's a BGR image. So therefore 2 corresponds to R. R. Then I have to display these two. So to displaying, I will use this code. Okay. So I will display this as im1, im, and in blue. So I should not make the mistake of just displaying that. I should always do the cv.convertColor. Convert color in cv.color BGR to RGB. This is the must, otherwise you will not be able to see the colors properly. So here also for this one also I will do that in blue. Okay. You can see the blue has been extracted. If you change this one, you can extract the red one, red plane and the green plane. I hope that's clear to you. Any questions? So I'll type some text here. Extracting the blue plane. Any questions? So anyways, all these things are there in the slides. So if you make a mistake, you can look at the slides. So we'll move forward. Is there anything that you want to know, or do you still need time, or can I move forward? Okay, I'll move forward then. Okay, so this we did. So we briefly looking at the cameras. So we will study the cameras in slightly more technical detail later. But right now, what we want to see is light is coming in like so, and then light goes through these lenses, and there is in those DSLR single lens reflex cameras, there is a mirror. This is that mirror. Item number 11 is the reflex and relay mirror. So usually light goes like that, and light gets reflected through that mirror and goes into the eyepiece. So you exactly see what the light coming through them, and if you retract this mirror, that light will strike this one. So exactly what you saw will go and strike. So here the item number 7 is the shutter. So you open the shutter, then and the mirror also is retracted, and then item number 5 you can see is the color and infrared filters. There is a filter here, and item number 6 is digital sensor. Then the sensor is there. So this sensor, you can see in front of the sensor there are filters, VGR filter. So that's the filter like that. Filter like that. Your sense array does not sense colors. Okay, it just has sensing elements. So because you have the filter on top, this pixel underneath this one, for example, only receives green light. Underneath this one only receives blue light because of the filters. So therefore your sensor senses some light, but we know because of the filter it's blue light or green light or red light. Sorry. Then this is how the sensor will sense different kinds of light, and then you can these empty areas are there. For example, here it's empty, here is empty, here is empty. Those you have to interpolate. This one is called demosaicing. So it is an operation that happens inside a camera. Any questions about the working of a DSLR camera briefly? Okay. So this is about color. I do not know too much about color. You can read this and understand a little bit about color. So there is a thing called color model, color space or color system. Facilitates specification of color, a coordinate system and a subspace within that system. So there's a coordinate system, but not all the colors cannot be represented. There is a limitation. Mm. So you can see the additive mixing. That's what we discussed, RGB. So you can see when you mix all three, you get red here. Subtractive colors that you remove from a piece of paper, when you subtract all three, you get black there. And the color resolution power of a prism you have seen, and in the electromagnetic spectrum, going to very long wavelengths with short wavelengths, then visible light region is very small. They are starting with 400 nanometers visible light ultraviolet to 700 nanometer infrared area, red colors. That's how the rainbow is formed. So RGB colors are used when you capture from a camera. CMYK and magenta, yellow, and black for printing. Hue saturation value HSV, how humans describe color usually. This decouples color and grayscale information, HSV. So for example, this is the HSV color space here, you can see. So you can see the hue means the color actually. It's green or yellow or red or pink or whatever. And in that, there is the value. So whether it's dark or bright. So if you take something here, it's bright yellow here, bright yellow here. And saturation means yellowness of that. So if it is mixed with white, it is at the center. It is yellow, but it's white like yellow. But if you go along that axis, the saturation axis, it is yellow. So this is the HSV color space. Sometimes it is useful. We have to convert that to different colors. So in open CVT color allows you to convert into different color spaces. Yeah. So in summary, a grayscale digital image is an array of 8-bit unsigned integers in 0 to 255. We call each integer a pixel. Color images have three such planes, one for red, one for green, and one for blue. We can manipulate an image using OpenCV function over a pair of for loops to access each pixel, which is slower. Okay. Then we'll move to the part of the sampling and reconstruction, which let's go through that fast, and then we will look at the point operations. So sampling and reconstruction is like this. So sample, for example, if you sample a simple sine wave, okay, simple sine wave. So you can see here the our sample is there. Okay, the black one is the actual sine wave. Another sample there, another sample there, another sample there. So you can see this sampling is not frequent enough. As a result, you can draw this gray sine wave along that. It is entirely different from the actual sine wave. So if you take a sine wave of high frequency and undersample it, you get this effect. A different sinusoid can be drawn along that. Information is lost, you can see. So surprising result is indistinguishable from a low frequency. Can you see? It's indistinguishable from a low frequency. So this is called aliasing, means signal traveling in disguise as other frequencies. So these things happen in sometimes in movies and so on. You see the wheel turning in the opposite direction, right? Because the shutter speed of the camera is the same as the wheel speed. It's called wagon wheel effect or the stroboscopic effect. So you can see the wheel is stopped here, right? You can see that wheel. You don't see the wheel moving. Yeah. So you can look at this. So this thing can happen. Okay. In images, they can happen. So it's a 256 by 256 image. If you lower the resolution, you see the these contents that you have to see actually start disappearing. So smallest content first, and then even large content start disappearing because of this aliasing. You can see that that's true, right? So here, here you get very different patterns created, right? You know that that this is like a tiles, but here weird lines get created here. So it has happened in this person's shirt also. And when you focus a camera on a computer, that happens. Yeah. So these things happen in the natural world. So people have studied them. This is one of those papers that studies that. You don't have to worry about that. Also, it can be very crazy actually. Let me try to play this. You can see the person's things are moving because of this aliasing. Can you see that? Crazy things happen. Okay. So this is you have to know about the Nyquist sampling theorem. I think most of you know that. When sampling a signal at a discrete interval, the sampling frequency must be at least twice the maximum frequency of the input signal to allow us to reconstruct the original signal perfectly from the sample version. So here this is bad. You can see this is this signal is of high frequency, but you are sampling at a lower frequency. So it's bad. But this one is okay. Is good. This sampling is good. So how can we get rid of aliasing? To get rid of aliasing, sample more often if you can. For example, if you take audio signals, you know that in CD quality you sample at 44 kilohertz. Why? What's the reason? The human voice can reach 22 kilohertz, 20 kilohertz. So if you twice means 40 kilohertz and slightly more than 40 kilohertz, 44 kilohertz. So that's the sampling rate of CD quality music. So more than twice the highest frequency. So otherwise you have to get rid of the frequencies that are greater than half the new sampling frequency. You have to have a filter and filter it out. We lose information, but that's better than aliasing. How to get rid of high frequencies? You can blur it. So you can have a low pass filter after the mic to do that. So yeah, I hope these things are general things that you know. So resampling and interpolation in the image domain. Okay, now let's see this subsampling and image. So what we want to do is assume that these are pixel locations. We want to subsample. How do we reduce the size of an image by factor of 2? We can, how about throwing away every other row and column like this? Is it okay? It is not okay, because if you do that, maybe if the image contained high frequency variations than what can be represented by this sampling, it will create aliasing. So therefore, before you do that, you have to smoothen the image. So you can see subsampling without pre-filtering. If you subsample without pre-filtering, you can see if you subsample too much, you can see crazy things happening to the image because you did not filter. So, but if you filter it out and subsample, generally it is okay. It's of course blurred, but it's okay. Crazy things has not happened. So here you can see the giraffe. So if you downsample by 4 without subsampling, you can see here the stripes are mixed with the fence. But if you downsample after smoothing, it's generally okay. Giraffe is generally okay. So then that is reducing the number of samples. But how do we increase the sample? That means how do we zoom an image? So let's increase the resolution of the sampling width. So we have to have additional pixels. So what is the way to do that? What should be this value here? So we need to so-called interpolate to do that. So therefore we mark, these are the centers of pixels. These are 0, 0, 1, 0, 1, 1, 0, 1. These are the pixel centers of pixels. If you, we know the values of those pixels. So to get this value, for example, you can add this one, and this one and divide by 2, right? Because it's at the very center. To get this one, you can add this one and this one and divide by 2. To get this one, you can add this one and this one and divide by 2. So this one also same. To get this one, you can add this one and this one and divide by 2. So this is how you can interpolate. So this is we call f.5 by 0.5. We can this f 0.5 by 0.5 half a plus b, you can say, right? For this one, how do you get this? Half a plus c. This a, b, c. This one, you can add all of them by divide by 4. Yeah. But this if you upsample by a factor of 2. But if you upsample by a factor of 3, then you have to properly ratio on these things. So this happens inside a camera. It's called demosaicing. I talked about it before. So the proper name for this is called bilinear interpolation more generally. So if you have A, B, C, D, it will find the value along AB here. It will find the value along CD here, and along this axis it will find the value that you require at this place. So you can see bilinear means it's drawing sort of a line between the pixels heights, considering pixels as heights, the drawing lines. So you can read about it more. So the formulas are there how to get this done, but we don't need the formulas. You can, when you think about it, you can get that working to subsample. So this is called bilinear interpolation. But there are other better interpolations called bicubic, cubic and bicubic. So I will show you that these functions are available in the GIMP. In Photoshop also these are available, but I use GIMP. So it will take some time for GIMP to open. It's a very good program. So open some image. So annoying thing with these kind of images is like opening a file. All these things are troublesome. But in Photoshop, they remember where you last opened and so on. So I have, wait a minute. Okay, let's open some image and I open this image, so I can. I think I should open a small image. Let me find a small image. Otherwise, it won't make sense to you. Small image. Second to find one. A lot of images are there. I like this image very much. This is the image of Arwen in Lord of the Rings. So we can image. We can image. We can scale image. You can see in the scale image, you have these scaling methods, cubic. So you can take linear. That linear is by linear. So I will increase the size to maybe 400%. You can see that, right? You can see that the 400% increased. Using bilinear. So if you increase image, scale image, if you increase using bicubic, it is better. 400%. If you get a bad image, very small image, you can see the effect very much. Yeah, you can see, maybe you can see the difference, it's much better. So these are methods that are there. So you can experiment by yourself using GIMP or something. Yeah, so we will not go through this, that's okay. So intensity transformations is what we want to do now. Okay, before doing that, let's take a small break. I hope that we can start at now it's 7:36. 7:50. Let's start at 7:50. 7:50. So starting time. So I will post the recording. Good evening. Thank you very much for being in the meeting. So we will continue with the intensity transformations. Also, I sent you a WhatsApp link over the Zoom chat for you to join. We create a small WhatsApp group if you want to quickly communicate. I hope I can still be heard. So we look at the so-called intensity transformations. These are the ones that change the intensity values. We tested one in the previous part of the class today by just adding 100, but that is a very simple one. So we will see other transformations that we can do. Now, in intensity transformation, the output value of the pixel depends only on the input value of that pixel, not its neighbors. That's the thing about that. So consider that this is an input image, and we had the intensity transformation, and this is the output image. So if you take some pixel here, the corresponding pixel in the output image only depends on this input image, not anything else. Those are called point operations. So if we consider input image as a fx, so fx you can see is, I have marked that here, intensities are from 0 to 255, and you can see gx Here, intensities are from 0 to 255. This is my fx input image. X is the location. This is my gx, the output image. Okay. So what this line means is, this blue line means if I have a pixel with intensity 100, what is the value of the output pixel? That's all. It's in this one, it's 100 because this is a identity transformation. This one is an identity transformation. So now a lot of things are there. So let me erase the ink. So you can see the way to do that is you open an image as usual. As you can see, we have opened the image here, call F. And then we have this T. This is my T, this transformation T. You can see NP array 256. What that means is it will give me an array of this nature. So that array. So when you do the Python tutorial, you will understand these things. So at the location 0, you have value 0. At the location number 1, you have value 1. At the location 2, you have value 2. And so on. At the location, last one is 255, as you know. 255. Location, the value is 255. 255. So it is input is the same as the output, as we can see here. So input value 150, you get the output value 150. That's the identity transformation. So that's why at each location you have the same value of the location inside the array. So that you can do in Python by writing actually NumPy by writing np arrange. Yes. And then the most important thing is this one. To get the resulting image, this is my original image F. This is the resulting image G. To get that, I have to only do this one. Very easy. So this T, assume that this T has been constructed like that. If I say T, let's take a location like 74. It has a value 74. Okay. So we have to listen carefully for this. If I say T74, what is the value located there? Actually, the value located there in this array is 74 itself. 74 itself. So if I put a value, pixel value inside this array, address that, I will get the output. So what I'm doing is I'm putting the whole image into the array. Whole image I'm putting into the array. You can see that, right? Then it will, for each pixel in the image, it will give the corresponding value. If this pixel is 100, it will give me the value 100. There's no use in that because it's identity, but this is the mechanism of applying that. This is the mechanism of applying that. Okay, so now let's do this identity transformation. Now I will use not Colab, I will use Visual Studio Code. I think I will, I have folders for the teaching. I will have a code folder here. So you will know how to do this when you go through that video of installing Visual Studio Code and so on. I will open this code folder. Okay. Then I'll create a new Jupyter notebook. So I will save it. is 26 to 7 in class. So the notebook is saved now. So it's like the Colab. I can open images. So I have to get an image for that. So you know that I have a lot of images somewhere. So I'll get those images. I will put them in a location that can be easily accessible. So I'm going to put this in a folder called images. Inside this, I'll create a folder called images, and I'll put an image there. So I put the image there. Okay, you can see that, right? In the code folder images. So import CV2 as CV. So I'm working on my own computer. So I have to. I'm using the Python. Yeah. I have installed Python and all these things I have done. So I hope that you will also do this. Okay. Import. Okay. Yeah. F equals cv.imread. Imread. It's in the images folder. Images mr.jpg. That's okay. CV imread grayscale. This is what I want. Okay. All right. That's so I will always assert im is not none. Okay, that's fine. Not im. F is not none. So now I have to create the transformation T. Np dot range 256 D type you intend. Okay. So this I do not want it. I want to plot this and see plt dot plot T. I will plot that transformation and show you what it is. That's the transformation you can see, right? From 0 to 255. So it's when the input is 0, output is 50. That's it. That's T. So to apply that T to get the image G, what I want to do is T and index with F. F is the input image. Now I have T. It's so easy. So fig X equals plt dot subplots. So I want to create 3 plots. Fig size is okay. Then X in 0, I want to X0, I want to plot T. And X1, I want to plot the original image. Im show F. Of course, you know that CMap was gray is required. And you need the Vmin and the Vmax. And then in AX1, I will plot AX1. I'm sorry, AX2, I will plot G. Okay. Annoying, this AI prompting is annoying, right? plt.show. Okay, let's see whether the transformation happens. So you can see this is the transformation. You can see nothing has happened to that. But if I change this transformation by somehow, maybe I put is from maybe 100 to 255, maybe end, 100 to end 155. I hope it is 25, 255. So I put 100 to, from 100 there, I put 255. Or maybe I put black, 0. Put them 0. So you can see bright pixels will be blackened out. See, can you see the bright ones are blacked out? If I control that transformation, I can do things to the pixel values. So if I put 255, all the bright pixels will greater than 100 will be. Yeah, so can you see that transformation is changing? So I hope you understand what this transformation thing is. So it is what an input value maps as the output value, and it is affected by writing G equals TF. It's so easy, so easy. I hope that it is clear for you. So maybe you can, if you have, you can take a screenshot or you can type it.
So can I ask a question? Is T like a user-defined data type, or is it a matrix?
Yeah, that's a good question. So T, we can put T and print it. So T, you can see, it has 255 numbers, right? See, 256 numbers. 256 numbers. So if you type T dot shape, you can see it has 256 numbers. That's all. So it is graph of that is this one. This is T's graph. So how did you create that? Using this command. This is the question that you have. What is NP arrange? Maybe maybe you do not know that part. It is perfectly okay because you did not go through the tutorial yet. So in that, so it is clearly shown here, right? So what that means and so on. When you go through the tutorial, you will understand what that means. So please, it is important to go through this tutorial. What you need to know right now is that we can create arrays using the nparrange command. So I have created that array. So it is 256 means 0, 1, 2, 3, 4 up until 255. That's what it is. Then after that, I am changing those values of that array. It is an array. Array is a placeholder, like what I drew here. So these are important questions actually. So I think I did not properly explain that part. So this T array, if you take T array, it's an array of 256 numbers. Why 256? Because we know that from 0 to 255, those are the 256 numbers in an image. So at 0th location, because of this command here, np arrange, it will put 0 itself. Okay, you can use a different numpy command to create that array. You can manually do it. At location 1, it will have 1. At location 2, it will have 2. At location, let's say 74, it will have 74. Finally, at location 255, it will have 255. That is that array. An array is placeholder that can be accessed using this index. So in this array, if I say T74, if I index it with the number 74, the value at the location 74, it will spit out. So it will see what is the value of location 74. Then it will notice, oh, at 74, I have 74. That will be spitted out. 74. That's what it does. So now, rather than you using a specific number, if I give the image itself, so you can see this is the input image, right? This is F, this is my F. If I give the full image itself, it will spit out numbers equal to the total number of pixels here. For each pixel, it will spit out a value. For each pixel, it will spit out a value by looking at the contents of that location. So in summary, once again, T is an array that we created using NumPy. It has 256 locations. It must exactly have 256 locations because the possible intensity values of the input image can range from 0 to 255. So 256 locations must be there. Otherwise, it will create a problem here. So for example, let's try that here. So rather than say 256, let's say I create an array of 100. I create an array of 100. Then if I try to comment that out, if I try to do that, it will be an error. You see, index 111 is out of bounds of axis 0 size 101. Can you see that? So the input image has contained a pixel with intensity 101, 111, and this does not have that many locations because I put a array of size 101. So I need 256 here. Then it will not be a problem. Yeah. But I can change those values here by doing different kinds of things. So maybe from 150 to 255. To 255, I put the 255. So therefore, this will look so like this. And you can see the bright pixels are fully widened out. All other pixels remain the same in color because of this intensity transformation. So yeah. So these are extremely important. It's especially important in medical image processing also. For example, if you have, I'll put a medical image. Into the folder. This one. Open that image instead. Open that image instead. Comment that out. So you can see if you run that. So we can see that those intensities that are in this region widening out. So maybe this is what the radiologist wants to see. He wants to remove those intensities, maybe brighter than maybe 200. He wants to blacken them out so that he can concentrate on some parts of the image. See? So like that, you can apply those things. You can see they are, although they are very simple, they are very powerful. Yeah, thank you for that question. So that gave rise to me saying this also. Any other questions? Okay. Yeah, let's move forward then. So you can see the value of intensity transformations. So also we can use this as this one. CVLUT is also the same thing as this one. Lookup table. It also can be done. This can be done using NumPy only as GTF. So what is T here? T is this the identity transformation. Identity is called identity because the output value is the same as the input value. Okay. Then we look at the negative transformation. This is the negative. So you can say 255 minus fx. This is the negative transformation. 1 minus that value, negative. So when you have 0, it will give out 255. If you have 200, it will give out 55. It will have 255, it will give out 0. So that's the function of the negative transformation. So at 200, it will give me 55, like that. So let's apply that. And I'll show you some magic. Okay, for that I need a special image, which I will copy. Okay. All right. So I'm going to apply another transformation and show you. But this time I will show using OpenCV windows. OpenCV. I will use Katrina. Okay. Okay, it's fine. So I want to use the negative transformation now. So negative transformation, as I have shown here, NP arrange 255. So this is a way of creating an array. Starting from 255, going 254, 253, like that. So you have to read this np arrange command in the tutorial and understand how that works. So I'm not doing that because we cannot go through the tutorial right now. It will take time. Okay, so that array is created. So I can even show you that array. I have the code to show that array. So I'll show you that. Okay, didn't run that yet. Okay, so this is that transformation. So you can see that one is a negative one, right? Negative transformation. Negative. I have to set the minimum maximum values of this. Sometimes I don't remember the commands. Okay. It's not. I don't know that. So that is okay. That is okay. Find that out later. You can see this is the negative transformation. So what I want to do is apply this, and I want to show that using OpenCV windows. Video team show G, video team show F. So you have to wait, and then TV dot team show G, and wait. Okay, now that's all. Okay, are we ready? I hope you are ready. So okay, yeah. Okay, so this is the window. Okay, yeah. I hope you are ready. I hope you are ready watching. Oh my goodness, can you see that? Yeah, it's crazy, right? I'll run that again. This is one. When you apply negative transformation, it's like that. You get scared. So I hope you don't get scared tonight. So you can see the negative transformation he applied by creating this array T. And T, you can see it's negative. Yeah, this display thing I cannot find out. Okay. Any questions about that negative transformation? Okay, but that's not all. You can change this transformation the way you like. So here I have created a very complicated one. You can see I have created a transformation with 3 line segments. 3 line segments. I will not fully explain how I have done that. So I have called C these coordinates, this coordinate here, this coordinate there, and based on those, I'm creating these line segments T1, T2, and T3. These 3 line segments I'm creating. So you can see the crazy commands I'm using. So those commands I will not explain. So it is up to you to please go through the tutorial. Then you will understand this little constructs in NumPy. And then I am concatenating T1 and T2. That concatenate means combining them. And then I'm combining with the T3 also here. After that, we can do the same thing. So here I'm using CVLUT, but you could have used the same thing, transform and put image original into that. So when you do that, different things can happen. By changing these coordinates, you can get different things to happen. So sometimes in medical image processing, you have transformation like that. For this input image intensity is F, output image intensity is D. They have a transformation like that, like this. 0 up to here, 255 from there, and then the linear scaling. So this is called window center operation. Intensity window. This is the center of that. So you can see the intensities from here to there are shown. Others you black them out or white them out. So that part the radiologist can properly see if you apply that transformation. So various things can be done if you manipulate this transformation T. That's all you need to know. Okay. Any questions about this? Okay, let's move forward. Please don't hesitate to ask if you have a question. Then there is one more intensity transformation called gamma correction. There also we do exactly the same thing. So you can see CVLUT, I said is equivalent to writing that as TM, right? This equivalent. It's the same. It's the same. So here I am using NumPy constructs. Here we are using OpenCV constructs. It's the same thing. So what is gamma correction? You treat these input intensities as 0 to 1. That means you have to divide the image by 255. So you can see in this one, I am showing from 0 to 1, not 0 to 55. So divided. And we take the input image and raise it to the power of gamma. Raise it to the power of gamma. So you can see if gamma is like 5, that means you get 0.2 to the power of 5, very small number. 0.8 to the power of 5. Generally okay. So if your gamma is 1, no change. If your gamma is like 0.2, 0.2 to the power of 0.2. So that becomes larger than 0.2. See, it has become larger than 0.2. Okay. So this is gamma correction. So let's take gamma greater than 0. Okay. Value of gamma such that from 0 to 1, those kind of gammas. What is the effect of that? We need to understand that effect of gamma values that are from 0 to 1. So that means a gamma value like 0.5. So you can see these are dark pixels, right? These are dark pixels. 0 to 0.2 means dark pixels. You take a certain portion of dark pixels and represent them using a wider range of dark pixels. So here it's 0 to 0.2. Here you can see 0 to 0.5 or something. So dark regions are enhanced in this case. So if you want to see what are the contents of the dark regions, you can use 0.2 for gamma. The opposite, if you take, for example, gamma equals 2, for example, if you take this different, so you can see here range of bright pixels. These are bright pixels. You can see this range is bright pixels is represented using a larger range of bright pixels. A larger range of bright pixels. Can you see that? It is good to enhance the bright areas. So dark areas are shown with darker values. Yeah. So here are examples of that. So this original image I have shown. This is the runway from Gonzalez book and gamma corrected ones. You can see areas that you can clearly see. So bright areas are vibrantly shown. So different values of gamma I am showing you. So if you take, for example, gamma equals 5, you can see the effect that we want has been achieved. The bright areas are vibrantly seen. Bright areas, these bright areas, you could not see much now. Now they are vibrantly seen. Dark areas have become even darker. Opposite effect if you have gamma like 0.2. So you need to understand what happens when gamma is less than 1 and when gamma is greater than 1. So these operations are very important if you want to do the pre-processing in an industrial system. Very simple operations, very fast, but very useful. Okay. I hope it is okay. Now let's briefly look at histograms. Now histograms is a very simple concept. It's not hard. Histogram is we go to those days when we go to school. Maybe the teacher will ask, okay, who are the people who have marks from 0 to 10? Okay, 0 to 10 marks. Okay, there's one student. Who are the students who have marks from 0 to 20? How many? Maybe you have that many, right? Maybe you have got 5 students with that. Who are the students who have marks from 0 to 30? Maybe again 5 students. Who are students who have marks from 30 to 40? Maybe again 5 students. 40 to 50. Maybe 6 students. Right? This is the histogram. Right? This is the histogram. So for images also we can do that, but for images it's not like 0 to 50. We have 0 to 255. How many pixels have intensity 0? How many pixels have intensity 1? How many pixels have intensity 2? And so on. Right? How many pixels have intensity 255? This is histogram, very easy, right? So we can represent the intensity distribution over the range of intensities using a 0 to 255 histogram. If H is the histogram of a particular image, HRK gives us how many pixels have the intensity RK. Maybe it's like 100. Like how many pixels have intensity? 100. That's what you're asking. The histogram of digital image with gray values in the range of 0 to L-1 is discrete function HRK, NK. NK is the number of pixels with intensity RK, where RK is the kth gray level and NK is the number of pixels having gray level RK. Okay, we can normalize this histogram by dividing by the total number of pixels, then it becomes a probability mass function. The histogram that we described here have L bins, but sometimes people decide to construct histograms with smaller number of bins. Okay, let's do this exercise of constructing the histogram of this 3-bit image. It's called a 3-bit image because values are from 0 to 7. So it's 3 bits. That means only 3 bits are there. So the maximum number it can hold is 1, 1, 1. That is equal to 7, right? Smallest number is 0, 0, 0, 0. Okay. So for this histogram, you will have 8 bins. Right? Bin number 0, bin with value 1, bin with value 2, bin with value 3, bin with value 4, 5, 6, and 7. Those are the bins that we have. So we have to count the pixels and put how many values are there. That's all. We can do that. Are there any zero values? Nothing. So therefore, it's 0. It's 0 intensity. It's 0. 0. Intensity 1. Nothing is there. 0. Intensity 2. There's 1. 1. What can you do for the other ones? You can in mentally you can do that.
No, I have a question. This when you say intensity, are you talking about the color between 0 and 255, or are you talking about something else?
Yeah, your question is correct. Color between 0 to 255. But in this image, this is a 3-bit image. Okay. So in this image, colors are only from 0 to 7 in this particular image. Otherwise, the colors are from 0 to 255 because I wanted to give you a small exercise. I decided to create an image which has maximum color 7. Maximum color is actually 255. Yes. Did I answer the question? Yeah.
Yes, sir. One more thing, like each cell, shouldn't it have 3 different colors? Like now here.
That's a good question. So this is a grayscale image. I should have said that, right? Yes. So
Then
the
it only
3 by
has one.
one color, grayscale.
So when you say grayscale, it's either black or white. Does it mean like that?
Grayscale, so it can values can be from 0 to 255.
One set of colors, is it? Or like
Yeah,
how
they're
would you?
just intensities. They are just brightnesses. So 0 means black, 250 means fully bright. They can have in between gray values. Right?
Okay, and that color, the full intensity is black color, which is just is it a single color when you say black color?
Okay, so it is just the brightness. There is no color.
All
There is no
right,
color. It's just the brightness. So
I guess the brightness. Okay.
yeah, just the brightness. So in the Colab, remember the very first thing that we did was creating that image. This one. When we created that image, we said NP068. This is a size 6/8 grayscale image. So if you put value like 100, it will appear as gray. If you put value as 255, it will appear as fully bright. That's the thing. One value, just intensity. It's a brightness from 0 to 255. 255 is the brightest brightness. 0 is the darkest darkness. It's only the intensity. There is no color in that. But if you take a color image, you can see you have to give 3 values, like you rightly said. You have to give the R, G, and B values. So here you can see the redness is too high, green and blue are low, so you see it as red. If you put it 0, you see it as different color.
So can you have a color image with different intensities?
Yeah,
Or
yeah,
is
of
it
course.
one?
Yeah. You can have. So now this is 0, so 255. So this is RGB, brightest green. This is the brightest green. Can you see that? So I can lower the greenness of that. I can put 100 here. So it is a dark green. Can you see that? If you put 50 here, it is a very dark green. Can you see?
Okay, got it now. So
Yeah. So only the green is changing. So these are very important questions. I'm glad that you asked these questions. So these, I mean, if you take the scheme for something, you can change this exactly. Exactly, these things can be changed. Um, so let's open some image and see. So this is the thing about GIMP. You have to go through the whole file hierarchy to open open something that you want. It doesn't happen in things like Photoshop. open this flowers. Flowers. So that image. I think I remove that image. It is a good image. I want to get that back. RGB flowers. Okay. So I open that. So then you can see colors. So then you can say, take the image and you can put the mode to a grayscale. Now it's a grayscale image. You can see different brightnesses are there. Mode RGB now. Okay. Now you can take the color curves. For example, curves. In these curves, you can take individual colors and adjust. Take the red value and adjust the bright reds. I'm making the bright reds dark. Maybe you are seeing that bright reds are becoming dark. Can you see that? Bright reds are becoming dark in that one. So these are the manipulations that people do with color. So these are very drastic manipulations I'm doing. So all three channels can be individually changed in a color image. But a grayscale image does not have those channels. It has just one channel. It's the brightness. So brightness is
Okay,
a
sir.
combination of the three colors here. If I have 255, this is a color image 255 and 255. It's fully bright. It will be just white. See? So color to grayscale transformation is a transformation. You have to use all three values and compute that. And there are color planes. So color is much more complicated. Okay, color is much more complicated. I don't understand color too much. So that's why I gave this slide and I didn't talk about it too much. So maybe this slide is enough for you to, I have given some links, go through this and understand what color means in slightly better way. So I can see the questions, so different color represent, all these things are there. So invest some time if you are keen about this. That's all I know about color. I don't know too much about color. Yeah. Getting back to the histogram, I hope I answered the question reasonably. So this is a grayscale image. So intensities are from 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. So you just have to plot the number of pixels in these things, these colors. So 0 pixels, nothing. Pixel with intensity 1, nothing. Pixel with intensity 2, 1. You can see that and you can count that, right? 1. Pixel intensity 3, this one and this one, right? 2. I'm not properly drawing it. 2. Actually, these things have to touch, okay? 2. And pixel intensity 4. And they have to be of equal size. I think you know that from all levels. Pixel intensity 5. 1, 2, 3. 3 of them. That's a histogram. Pixel intensity 6, 2, 7, 6, 3, 7, 1. That's a histogram of that. That's the answer to this question. It's very simple. Okay, so we can get image properties through histograms. If the image is dark, histogram will have many values in the left region that corresponds to dark pixels. Now that kind of histogram is like that. Pure histogram. This is 0 intensity is 255. We are finding the number of pixels in that histogram. So if your dark image will have a histogram like that. If the image is bright, this one, if the image is bright, the histogram will have many pixels toward the right, toward the 255 area, 0, 255. This area, that's a bright image. So you have two model histograms also, bimodal histograms. Significant number of pixels are dark and significant number of pixels are bright, maybe like that. Okay. The two-mode histogram. A flat histogram is a vibrant image. These kind of images are nice. All the pixels are sort of equally represented. All intensity values are equally represented. So these are nice. So the photographers try to get that kind of images. So the auto correction options that you have in Photoshop and so on is something like this. Not exactly that, I think. Choose deep learning, I think. Something like that if you use autocorrect in your Photoshop and Science or software. So that one is in simple terms, if you can do that, called histogram equalization. Photographers like to shoot pictures with the flat histogram, such that pictures are vibrant. Histogram equalization is a gray-level transformation that results in an image with a more flat histogram. We can take an image and make it histogram flat by using an operation called histogram equalization. So we'll look at that histogram equalization. I have given you only two equations. So this is the equation that you should use for histogram equalization. This is very simple. So you are adding pixel values from 0 to k. And each transform value is that one times L minus 1. L is 255, 256. Okay, this is the total number of pixels in the image. L minus 1 divided by mn, cumulative sum of number of pixels, Lj, of the histogram. Okay. So suppose we do an exercise, then you'll understand this. Suppose that a 3-bit image L equals 8. Okay. For a 3-bit image, L is equal to 8 because the maximum number of intensity is 8. Number of intensities is 8. So maximum intensity is 7. Of size 64 by 64. That means total number of pixels is 4096. Has intensity distribution shown in the next table, where the intensity levels are in the range from 0 to L minus 1 or 0 to 7. Carry out histogram equalization. Okay, let's do that here. Okay, what we want to do is histogram equalization. Remember, we had in the equation summation nj, j goes from 0 to k. With the calculator, we fortunately have a calculator here. Okay, so in this one, we have to sum from 0 to 0. That means only this one. So this will be 790. Okay, this one should get up to 0 to k, 0 to 1. That means you have to sum this and this. That means 790 times 1023. 790 plus 1023. That will be 1830. Very simple. What is the value here? You have to add all three values, right? This, and this you have to add. But you can add this one and this one to get that value, right? So 1830 plus 850. You get 2662. Very easy. What's the value here? Add 656 to that. 3319. Then add 329 to that. You get 3648. Add 245 to that. 3893. Add 122 to that. 4015. Add 81 to that. You get 4096. That's the total number of pixels. Any questions about this? Okay. Then what you need to do is to multiply by the L we said is 7, Mn is 4096. This value you have to multiply by 8 and divide by 4096. 790 times 8 divided by 4096. You get 1.542. 5, 4. If you round it, you get 2. Then next value will be you have to divide 1813 multiply by 8 and divide by 4096. You get 3.540. When you approximate it, you get 4. Round it. Then we have next value 2663, and you get 5.20. 2012, approximate it, round it, you get 5. So what that means is, if your input intensity value is 0, you map it to 2. If your input value is 1, you map it to 4. If your input value is 2, you map it to 5. That's your T. So histogram equalization is also an intrinsic transformation. You can do it like this, or you can use the OpenCV function. Here is the completed table. So this is the mapping that we have. So now there is a quiz available. Maybe I can extend the time for you to do that. Meet 2:30 is wrong. But I will show you the output of this. So histogram equalization, you can do that equation that I showed you manually, or use cv.equalize hist. If you give an image, this dark, like washed out image, you get a very nice histogram equalized image. Right? It becomes very nice actually when you histogram equalize. Now you can use the formula also. Here I am showing how to use the formula manually. So you can see exactly L minus 1 divided by Mn, and that summation, we call it CDF. Okay. So, but I have not showed you how to do that. So in summary, basic digital images, color images, we looked at grayscale images, color images, creating an image in Python, displaying images, increasing the brightness, and we looked at image planes. And we looked at intensity transformations. They look like G equals TF. T decides what it looks like. And then we looked at the identity transformation, negative transformation, intensity windowing, gamma correction, histograms, and histogram equalization. That's all we did tonight. I'm sorry. So let's do the quiz now. You can, I will extend the time for the quiz a little bit because now it's too late maybe. So yeah, it's another quiz. It's also very easy. Oh, what happened? Indeed. Quiz number 2. Can we try? Oh, some people have already done. What happens when you subsample an image without pre-filtering? Image becomes sharper, file size increases, high frequency components are preserved. Aliasing of artifacts may appear. That's the correct one, right? So next one. What is aliasing in images? Overexposure in bright regions, duplicate pixel values, high frequency signals appearing at low frequencies. This is the one. What is bilinear interpolation used for images? Estimating values between pixels, image smoothing, adding random noise, histogram equalization, color balancing, estimating values in between pixels. So like that, these 10 questions are very easy. You can quickly do them. I will increase the time limit a little bit so that you have a little more time to do. But I think it's very simple. But one thing is, please do not use ChatGPT. But read the question and select something. You can discuss with others. That's okay. But even if you put ChatGPT, please read it and understand and do it. Otherwise, it's just a waste. Also, as homework, you must do the Stanford Python NumPy tutorial. Please join the WhatsApp group. I put the WhatsApp group link here in the Zoom chat. I hope people have joined the WhatsApp group. Some people have joined. Yeah, not all have joined. So please join the WhatsApp group. Yeah, send the link to the WhatsApp group in the Zoom chat. Please join that. I will send it again. And do the quiz also. So if you have any questions, I can answer. Otherwise, you can do the quiz on your own. You can log off now. Thank you very much for joining. Have a pleasant rest of the weekend. Thank you very much for joining a class on a Saturday evening, late night. I will post the recording.